We end tonight with the clearest pictures yet of Neptune, the most distant planet in our solar system. Take a look. The striking infrared images were taken this summer by the James Webb Space Telescope. The James Webb Space Telescope had been surveying the outer planets with its piercing infrared vision when it captured something so unexpected that astronomers were left momentarily stunned. In the data streams that poured in from the edge of the solar system, Neptune, an ice giant bathed in the faint sunlight nearly 30 times farther from the sun than Earth, displayed a signature that could only mean one thing. Something massive had just collided with it. The shock waves of that moment rippling through the gas and ice of the planet's atmosphere were written into the thermal patterns and spectral lines Webb observed, offering a rare glimpse into an event of staggering cosmic drama. To stay updated on discoveries like this, please like and subscribe for more content. Neptune has long been a planet shrouded in mystery. Despite being the fourth largest planet in the solar system, its distance and faintness have kept it relatively unexplored. The Voyager 2 flyby in 1989 gave humanity its first close look, revealing turbulent winds, immense storms, and a deep blue hue born from methane in its atmosphere. Since then, astronomers have relied on ground-based telescopes and, more recently, the Webb telescope to track its weather patterns and study its faint rings and moons. But never before has humanity witnessed a direct collision on Neptune itself until now. The Webb data revealed not only a sudden burst of heat rising through the atmosphere, but also chemical fingerprints suggesting that foreign material had been injected into the planet's skies. The residue of a wandering object that met its end against the immense gravity of the ice giant. To understand the magnitude of such a collision, it helps to picture the size and scale of Neptune. With a diameter almost 4 times that of Earth and a mass 10 times greater, its gravitational field dominates its corner of the solar system. An object large enough to leave a visible mark on such a planet is not a small asteroid, but something far more substantial. The Webb data indicated the intruder could have been a body tens or even hundreds of kilometers across, possibly a rogue icy object from the Kuiper Belt or a stray comet dislodged from the solar system's outermost reservoirs. The sheer violence of its impact, though absorbed by Neptune's thick atmosphere, must have released energy on a scale impossible to truly grasp, rivaling millions of nuclear explosions unfolding simultaneously. The collision itself would not have looked like the familiar fiery impact we associate with rocky planets such as Earth or Mars. Neptune's atmosphere, composed primarily of hydrogen, helium, and methane, is a dense, shifting ocean of gas and ice particles. As the object plunged inward, it would have compressed the atmosphere in front of it, creating shock waves that spread outward at supersonic speeds. Instead of cratering the surface, because Neptune lacks a solid surface in the conventional sense, the intruder would have dissolved and fragmented, injecting its own material into the swirling hydrogen seas. Webb detected sudden enhancements in carbon-based molecules and unusual spectral lines that hinted at exotic ices, possibly ammonia or carbon dioxide, that had been carried in by the foreign body. This chemical scar may persist in Neptune's atmosphere for decades, a lingering testament to a brief but monumental encounter. One of the most remarkable aspects of this detection is that it underscores the dynamic and hazardous nature of the outer solar system. For decades, Neptune has seemed a distant and tranquil world, serenely orbiting far from the chaos of the asteroid belt and the storms of Jupiter. Yet the Webb telescope has revealed that even here, nearly 3 billion miles from the Sun, collisions still occur. The solar system remains an active, evolving place where icy wanderers travel on unstable orbits and occasionally plunge into the grasp of the giant planets. What Webb witnessed was not a relic of the solar system's violent formation, but a contemporary event, a reminder that planetary impacts are not just ancient history, but an ongoing reality. The implications extend far beyond Neptune itself. Observing such a collision allows astronomers to refine their understanding of how impacts shape planets both in our solar system and beyond. Impacts are a fundamental driver of planetary evolution. They deliver volatile compounds, stir atmospheres, alter orbits, and sometimes even strip planets of their outer layers. On Earth, impacts have reset the course of life more than once. From the asteroid that ended the reign of the dinosaurs to earlier collisions that may have brought water and organic molecules to the young planet. On gas and ice giants, the role of impacts is less well understood because the lack of a solid surface makes direct evidence harder to find. But Webb's detection of this event gives scientists a rare chance to study what happens when a massive object plunges into a gaseous planet, a scenario that may be common in exoplanetary systems across the galaxy. The energy released by the collision would have penetrated deep into Neptune's layers, potentially disturbing its atmospheric circulation. Neptune is already known for its ferocious winds, which can reach speeds exceeding 1,100 km/h. The injection of heat and momentum from the impact could have stirred these winds into even more chaotic motion, generating temporary vortices or enhancing existing storms. Indeed, Webb's subsequent images revealed unusual bright spots and disturbances in Neptune's cloud bands, structures that seem to rotate and elongate in patterns unlike the familiar storms tracked in recent years. These may represent the atmospheric echo of the impact, fleeting structures sculpted by the turbulence unleashed in that cosmic collision. For planetary scientists, the chemical aftermath is perhaps the most valuable prize. Webb's instruments are capable of dissecting light into incredibly fine detail, allowing astronomers to identify the presence of molecules at parts per billion levels. The detection of unfamiliar compounds in Neptune's upper atmosphere suggests that the impactor carried unique materials into the planet. Studying these signatures can reveal the composition of the colliding body, effectively turning Neptune into a natural laboratory for sampling material from the farthest reaches of the solar system. If the object came from the Kuiper Belt, its chemistry may represent a time capsule from the early solar system, a remnant of the primordial disk that formed the planets. By crashing into Neptune, it has ironically made itself far easier to study, its ingredients dispersed and glowing in infrared light under Webb's gaze. The sheer improbability of witnessing such an event adds to its significance. Collisions on Neptune are thought to occur, but their timescales are immense, ranging from centuries to millennia between large impacts. That Webb happened to be watching at the right time, underscores the telescope's value as a sentinel of cosmic activity. Unlike Earth-based observatories, which struggle to peer through our turbulent atmosphere, Webb's vantage point in deep space allows it to capture fleeting events with clarity. It is not only a tool for gazing at the most distant galaxies, but also a vigilant observer of our own cosmic backyard. This discovery reinforces the telescope's versatility and hints at the surprises it may still uncover as it continues to monitor the planets. The event also raises intriguing questions about Neptune's role as a gravitational gatekeeper of the outer solar system. Neptune's orbit sits just inside the Kuiper Belt, a vast reservoir of icy bodies left over from planetary formation. Over billions of years, Neptune's gravity has sculpted the orbits of countless objects in this belt, trapping some in resonances and ejecting others into interstellar space. The collision Webb detected may be a direct consequence of this gravitational influence. By nudging an object inward, Neptune sealed its own fate, becoming the target of the very body it had destabilized. In this way, the impact is a reminder that the planets and small bodies of the solar system are locked in a constant dance of cause and effect, shaping one another through subtle gravitational tugs and occasional catastrophic encounters. For those studying exoplanets, this collision provides a vivid parallel. Many of the planets discovered around other stars are gas and ice giants, like Neptune, orbiting far from their parent suns. The processes that shape these worlds are likely similar to those at play in our own system. By observing a real-time collision on Neptune, astronomers gain insight into phenomena that may also occur on these distant worlds where impacts could alter atmospheres, trigger storms, or even influence the potential for moons to host life. The Webb telescope, capable of probing exoplanet atmospheres with the same precision it brought to Neptune, can now apply lessons learned from this event to interpret signals from alien systems. Every spectral fingerprint, every trace of collision chemistry detected on Neptune becomes a key to unlocking the secrets of worlds light years away. Another profound implication of the collision is its relevance to the study of planetary defense. While Earth is shielded from many space rocks by the gravitational pull of Jupiter and Saturn, the outer planets demonstrate that impacts remain a fundamental part of solar system dynamics. Seeing Neptune absorb the energy of a massive collision serves as both a warning and a reassurance. On the one hand, it shows the destructive potential of wandering objects that cross planetary orbits. On the other, it highlights the protective role of giant planets, which act as cosmic vacuums, sweeping up or deflecting debris that might otherwise threaten the inner worlds. Neptune's collision is a reminder that the safety of Earth is partly owed to the sacrifices of the giants, whose gravity ensures that many dangerous wanderers never reach our neighborhood. As astronomers pore over the reams of data, new mysteries are already surfacing. Some of the spectral features detected by Webb do not correspond neatly to known compounds, suggesting that exotic reactions may have occurred as the intruder's material mixed with Neptune's unique atmospheric chemistry. These reactions could produce molecules rarely seen elsewhere, providing fresh avenues of study for astrochemists. The thermal glow observed by Webb also showed unexpected persistence, indicating that the impact's energy penetrated deeper than anticipated, perhaps into Neptune's enigmatic interior layers. where superionic water and exotic ices exist under crushing pressure. These insights may eventually help answer one of the great questions about ice giants. What lies beneath their turbulent atmospheres, and how do their interiors evolve over time? The collision Webb recorded is not just a singular event, but part of a much larger story about planetary evolution and cosmic interconnectedness. Neptune, once thought of as a remote and static world, has revealed itself as a stage for dramatic encounters that remind us of the solar system's ongoing vitality. The Webb telescope, by capturing this moment, has transformed an abstract possibility into a tangible reality, giving scientists a front row seat to one of the universe's most fundamental processes. Collisions build planets, reshape them, and sometimes destroy them. They are both destructive and creative, erasing old structures while sowing the seeds for new ones. In the violent meeting of a wandering body and a giant planet, we see the same forces that shape the Earth itself and continue to shape the cosmos. This discovery will be studied for years to come, not only as a record of what happened on Neptune, but also as a window into countless unseen events scattered across the galaxy. For every collision we witness, thousands more occur unobserved, hidden in the vastness of space. Yet, thanks to Webb's extraordinary capabilities, one such event has been brought into the light, allowing humanity to witness the raw mechanics of planetary change. Neptune's collision is both a revelation and an invitation, a reminder that the cosmos is alive with motion and that even the most distant worlds are still writing their stories in fire and ice. The Webb telescope's discovery of a gigantic collision with Neptune is only the beginning of what such an event can teach us. To extend beyond the immediate spectacle, one must consider the planetary environment into which the collision occurred, the fragile balance of Neptune's orbiting moons and rings, and the broader astrophysical questions that arise from seeing a giant planet struck in real time. Each thread of this narrative opens new avenues for exploration, bringing into focus not only Neptune's nature, but also the dynamics of the solar system as a whole. Neptune is often overlooked compared to Jupiter and Saturn, yet it holds its own unique set of mysteries. Unlike Jupiter's thick belts or Saturn's iconic rings, Neptune projects a subtler face to the cosmos with faint arcs of rings and a dynamic atmosphere that hides more than it reveals. Into this world descended the massive intruder that Webb detected, and the implications ripple outward to every object bound to Neptune's gravity. Its 14 known moons, led by the enigmatic Triton, may have felt subtle shifts in their orbital environments in the wake of the impact. Even though the energy dissipated primarily into the planet's gaseous envelope, the redistribution of mass and heat within Neptune could, over time, alter its gravitational field ever so slightly. This might influence the orbits of its moons in ways too fine to detect immediately, but significant over centuries. For scientists, it presents a tantalizing opportunity to track Neptune's moons with greater precision and to test whether impacts can indeed induce measurable changes in planetary systems. Triton deserves special mention in this context. This moon, larger than Pluto, is itself thought to be a captured Kuiper Belt object. Its retrograde orbit is a clue to this dramatic past, marking it as an outsider drawn into Neptune's embrace long ago. In many ways, the collision Webb observed can be seen as a repeat of this narrative on a smaller scale. Another outsider plunging into Neptune's grasp. Triton's surface, which is geologically active with geysers of nitrogen, might hold chemical or orbital traces of disturbances induced by Neptune's periodic interactions with wandering bodies. If so, Webb's detection of the recent impact is a modern echo of ancient processes that shaped Neptune's family of moons billions of years ago. It underscores the continuing role of collisions in sculpting the architecture of planetary systems, not just in their formation epochs, but across cosmic time. The rings of Neptune also enter the discussion. Though faint compared to Saturn's brilliant system, Neptune's rings are fragile, dusty arcs that seem to shift and fade mysteriously over time. A massive collision with Neptune could easily scatter material into orbit, potentially feeding or altering these tenuous structures. Webb's infrared eye might soon reveal fresh dust populations or brightening arcs in the ring system, the silent residue of the impact's debris. This raises questions about the origin of rings more generally. Could many ring systems across the solar system have been seeded or replenished by impacts of wandering bodies? Saturn's rings, while unique, might not be the only ones born of catastrophe. Neptune's recent collision offers a live case study for testing the connection between impacts and ring dynamics. From an astrophysical perspective, what happened at Neptune also resonates with theories about planetary system stability. The outer solar system is not a static place. It is influenced by resonances, gravitational scattering, and long-term orbital migrations. The very existence of the Kuiper Belt testifies to this, as does the presence of extreme trans-Neptunian objects whose orbits hint at past upheavals. A massive body striking Neptune is more than just chance. It suggests a chain of gravitational nudges stretching across the solar system, a subtle choreography that guided the impactor inward. Scientists studying orbital mechanics will look to model how such an object could have been delivered to Neptune's path, whether by resonance, interactions with Neptune itself, long-term perturbations from passing stars, or chaotic scattering within the distant Oort cloud. In this way, the collision is not just a planetary event, but a window into the deep dynamics that keep the solar system in motion. The energy of the impact also raises profound questions about Neptune's interior. While we often picture gas and ice giants as uniform spheres of hydrogen and methane, their insides are far stranger. Beneath Neptune's atmosphere lies a mantle of water, ammonia, and methane in exotic states. Superionic water that behaves like both liquid and crystal, ices that conduct electricity under immense pressure, and layers that generate Neptune's bizarre tilted magnetic field. A collision of the magnitude Webb observed could have penetrated these layers, disturbing convection currents or triggering unusual mixing. Though we cannot see these depths directly, the aftermath may be traced in changes to Neptune's magnetic field, auroras, or thermal emission. Already, Neptune is known to radiate more heat than it receives from the Sun, suggesting internal energy sources that remain poorly understood. By perturbing this system, the impact may have provided a natural experiment in planetary physics, temporarily altering heat flows and magnetic structures in ways that can be studied as Webb continues its observations. Exoplanet science gains new dimensions from this event as well. Astronomers have cataloged thousands of worlds orbiting other stars, many of them ice and gas giants resembling Neptune in mass and size. Yet the details of their atmospheres and evolution remain obscure. One of the challenges in exoplanet studies is understanding the role of stochastic events, rare but powerful processes like collisions in shaping planetary appearances. A hot Neptune observed in another system might display spectral signatures or atmospheric anomalies that result from an impact long past. Without a reference in our own solar system, such anomalies might remain mysterious. Now, with Webb's detection of a Neptune collision, scientists can build a library of impact fingerprints, sudden chemical enrichments, irregular heat emissions, or transient cloud formations. These can be used to interpret data from distant worlds, bridging the gap between theory and observation. On a more speculative front, the impact on Neptune also highlights the possibility of cascading effects through the outer solar system. Neptune shares its domain with countless icy bodies in resonant orbits, many of which are stabilized by its gravity. If an impactor was drawn from this population, others may follow similar pathways in the distant future. Could Neptune experience multiple collisions over cosmic timescales, gradually accumulating material from the very region it shepherds? This cycle of capture, collision, and assimilation might even contribute to Neptune's anomalous properties, such as its unexpectedly strong winds or peculiar thermal balance. Each impact could serve as a tiny nudge to the planet's evolution, invisible on human timescales, but decisive over billions of years. Beyond planetary science, there is the philosophical weight of witnessing such an event. Collisions remind us of the universe's indifference to permanence. Worlds can be serene for eons only to be reshaped in an instant. For humanity, tucked safely on Earth, these distant spectacles offer both perspective and humility. They show us that the forces that once battered our own planet still operate elsewhere, ceaseless and impartial. Neptune's collision, caught in exquisite detail by Webb, is not merely a scientific curiosity, but also a testament to the ongoing creativity and destruction that governs the cosmos. Every planet, no matter how remote, remains a participant in this endless cycle. For Neptune itself, the story may not end with the impact. As the planet recovers, scientists will be watching for long-term consequences. The redistribution of chemical compounds could alter cloud structures, perhaps spawning new storm systems. Heat injected into the atmosphere could rise, cool, and cascade into turbulence, sustaining disturbances for decades. The faint rings may brighten or darken. Moons may display subtle orbital wobbles, and auroral displays may intensify under the shifting magnetosphere. Each observation becomes a data point in a grand natural experiment, one that no laboratory could hope to replicate. Webb has not just captured a moment, it has triggered a campaign of study that will continue for years, perhaps lifetimes. The event also underscores the importance of continued exploration of the outer planets. For decades, Neptune has been a distant enigma, glimpsed only fleetingly by Voyager, and then left to the patience of telescopes. This collision argues for a return mission, a dedicated orbiter that can witness Neptune's dynamic processes up close. If Webb can see so much from nearly a million miles away at Lagrange point 2, what could a probe in Neptune's orbit reveal about the ongoing consequences of such an impact? It is likely that future missions will carry this question forward, inspired by Webb's discovery to demand a closer look at the eighth planet. The broader narrative ties back to planetary defense and cosmic hazard assessment. While Neptune bore the brunt of this collision, the event demonstrates the kind of violence that can occur throughout the solar system. By studying Neptune's impact, scientists refine their models of how bodies travel inward from distant reservoirs and how often they might intersect with Earth's orbit. Neptune's sacrifice is not merely academic. It provides vital data for protecting our own planet. Understanding how gravitational interactions shepherd bodies into planetary collisions allows us to better anticipate and perhaps prevent similar fates closer to home. There is the cultural dimension of such a discovery. Humanity has long mythologized the heavens, from Neptune himself, god of the sea, to the comets once feared as omens. To see Webb capture a titanic collision on a planet named for a deity is to feel the resonance of myth and science converging. The gods of old may not hurl tridents across the sky, but the cosmos still stages spectacles of awe-inspiring power. As the story of this impact spreads, it will no doubt inspire not only scientists, but also artists, writers, and dreamers who will weave it into humanity's collective imagination. In this way, the event transcends data and enters the realm of meaning, reminding us that exploration is not just about knowledge, but also about wonder. Neptune's collision therefore stands at the intersection of science, philosophy, and imagination. It is a singular event that enriches our understanding of planetary systems, fuels our anticipation of future discoveries, and deepens our appreciation of the universe's grand narrative. The Webb telescope has revealed something colossal, but in doing so, it has also opened countless new questions. Each one points to the vastness of what remains unknown, the immensity of what awaits discovery. Neptune, once thought distant and static, has become a living stage where cosmic forces play out before our eyes. And thanks to Webb, we are no longer spectators from afar, but participants, witnesses to the unfolding drama of the solar system. The Webb telescope's glimpse of a monumental collision on Neptune did more than spotlight a planetary drama. It cast a wide net of implications across science and human curiosity. With every new layer of inquiry, new perspectives emerge, and each angle sheds light on facets of Neptune, the solar system, and the universe at large that often remain hidden. Expanding further into the event and its meaning allows us to step into speculative yet scientifically grounded territory. The potential effects on Neptune's lesser-known moons, the analogies this offers to ancient planetary formation, the lessons it teaches us about habitability in harsh environments, and even how it could influence the way humanity organizes its priorities for space exploration. One intriguing area of study is Neptune's smaller moons. While Triton commands the spotlight with its size and retrograde orbit, Neptune also hosts numerous tiny, irregular satellites, many of which are barely resolved even with modern telescopes. These moons are thought to be captured objects from the Kuiper Belt, fragile wanderers bound by Neptune's pull. The shock of a major collision with Neptune could subtly alter their orbital alignments,